Hi, everybody. I come to the next section of physical database modeling. We jump into the next chapter, chapter 3, which is called variation modeling, and somehow try to reduce the problems of this general physical model. So we learned last time about the bond graph, all these non-causal modeling strategies and urban circuit modeling, all these. Perhaps we start with one of the general motivations at the very beginning. So what is the strength of the network analysis? It's somehow mainly the interconnections explicit. I'm showing what the information is transported from one position to another, from one subsystem to another. What kind of energy is exchanged between these? This is very well depicted in this network approach we learned in the chapter 2. However, if we want to introduce the equations, the various equations which are now necessary for control design, it's necessary to get the equations and not all these intermediate flows and variables, all these things. This is important for perhaps design questions like, well, how huge is the force as counter force on the ground? So remember my examples from Thomas Seifried's work on how to do this automatic revision of oscillations in generated distance. That's one question. Usually, you as a control engineer, you're just in some sort in the state space system. So at the very end, you have to collect all the equations, and you have to do these equation solving and all these things. And well, you're not so much interested in the intermediate flows, which you've got so all effort variables. That's perhaps the main driving force for our next way of how to describe a system, and this is the driving force. This is some sort of motivation. So we want to avoid to calculate all the constraints. This is our aim, and this is one part. This is the more practical position and more practical view of reducing the number of calculations, because failures have from all these. There's a second aspect which I want to highlight. We gain understanding into system dynamics a little bit more if we look at this chapter, because in the last chapter we learned already, okay, which components are responsible for the network dynamics at the very end. These are the storage elements, and then we learn something about, well, this dependent storages, and learn that all storages are state-based variables. So, and this is perhaps also something which is important, that there is some sort of connection between energy and the storage, and energy as the state-based variable. So we want to learn more deeply what the state-based system, how the state-based system is generated. So the aim of this chapter 3 is twofold. One is getting rid of the various calculations, and second, and to gain more understanding about system dynamics, how it's generated, what are the ingredients, what are the main driving forces, and this is all about the variation modeling. We can solve it like this. This is the chapter which is traditionally taught in theoretical mechanics. So if you learn something, if you're a mechanical engineer, you have to learn something about that. the interesting fact is, and they usually do not like it. So, because they learn it in the third semester or second semester, no, I think it's the third one, and then it's somehow, well, from a theoretical perspective, a little bit more abstract, sounds strange, etc. So, mechanical engineers sometimes fear of the chapter. But you're in master and you learn already something about more abstract things like optimization and those kind of mathematics. So you shouldn't fear of this. So don't believe in mechanical engineers. It's a bachelor degree level. So here we try to show you, well, it's easy, or I would say it's the easiest way to do the model. But if you look at the area that the conrads sound, they appear a little bit strange at the very beginning. But if you do it in practical way, it's easy. So that's my whole position. Okay. So, and that's very often in mechanics it's called Lagrangian mechanics, and we will see why it's called Lagrangian of mechanics compared to classical Newton mechanics of what we did before, but in a method paradigm. That's the difference. So, okay. We know already that, and this is important right now, that every energy storage element is responsible for the dynamics. So it makes sense at the very end to say, okay, we associate to every energy storage element some sort of variable. In the last chapter, we said, okay, it's a effort flow perspective. Now we look more on the geometric perspective, looking at the displacements and impulses itself. So on the integrated flow of effort, remember, if we integrate flow, being the impulse flow as the supports it, we get the impulse of the integrated variable. If we integrate effort, we get a displacement. And therefore, I say it's a geometric perspective, because if we look at this, all the variables defining where the x values are, you have some sort of geometric picture of the entire system. Very often, this kind of technical modeling is also the geometric perspective of a mechanical system, perhaps. In mechanics, it makes very much sense because the displacement in all the coordinates, if you have a three-dimensional object, for example, then you can draw the overall manifold where this object moving on or so. So, for example, look at we will have this example. Right? So, on some next slides. So important, we start there with the so-called redundant coordinate system, because we already know from our last consideration in chapter 2 that there might be dependent variables, and so it makes sense because we know all the coordinates with the tilde, just to be aware of the situation that there might be there are some coordinates which can be expressed by other coordinates. That's important. But instead of looking at the flow perspective or effort perspective, we now look at the integrated solution. And I want to talk about this redundant situation in a second. So here is my example. Think of the pendulum. Look on the right-hand side of the slide at the bottom. Think of a pendulum. What is a pendulum? The pendulum is a free moving mass which you force to just rotate or move around a circle. If you look at this is a different description, isn't it? You can say, okay, you can describe the movement of the body here, of the mass. Think the connection is massless in two ways. One way is you describe the forces. So there is gravitational force. You describe it in the Newton way, so in the flow way. The force is the gravitational force. You have acceleration towards the outer space, and then you calculate the equilibrium of the forces, and then you get the equations of motion. That's what we did before chapter 2. You can also say, okay, it's a similar or the different description is, well, we know that if I take a point mass, it can move in x and y direction, and I constrain the directions in that sense that we know it's it just rotates on a circle, or if you have a three-dimensional pendulum, it rotates on a ball. And then to constrain it has to rotate on a circle. It's like, okay, there's a constraint. This is nothing new for you because, you know, constraint optimization, there are always constraint in physics, etc. And we have here the very same thing. And that's the beauty of this approach to say, hey, very often in many applications, I know the constraints by just simply empirical evidence. So it's evident in that way that you look at the object and say, okay, it's rotating on a circle. Okay, that's problem. So it's a free movement mass with constraint to rotate in a circle. Let's look at what we can do with it, with this consideration. So obviously, but when we do that and say, okay, if we look at the free movement of mass, we have two points in a plane. Okay, so just constrained to x and y. Then we have two coordinates to describe the movement of the mass, right? X and y. So you have to know x and y position to define where the mass is. And you have, in addition, to know what the speed of the mass is to describe the entire system. Okay. So also in x and y direction. And with that, you know, a free movement mass, a point quantity, is only describable with 4 state-based variables, right? Now let's look at the pendulum. If you force and say, okay, it's a free movement of mass, but it's constrained to a circle. I say I cut one variable off, right? This means it's just one dimensional. If I just stay on the circle, I have just one dimension. And that's why, obviously, it's easier to say, okay, to stay on the circle, it's easier to say, okay, we use a coordinate system which is rotational, so one which is giving the radius and the angle to describe the position of the mass. And if I now fix the radius to be, for example, L1, because that's the definition of the movement of the pendulum, then the description becomes simple and then I have just one coordinate. And that's how you describe it. But you can also describe it in XY direction, something for homework, if you like to do it. At the very end, please do the calculations in XY directions and constrain it to a circle. And you know, describing the circle means r squared is equal to x squared plus y squared is the same definition. It's the very same, but it's not that beautiful. If you do the calculation, please see all the calculations there follow. It's the coordinate system here is easier to use. This rotational coordinate system, so polar coordinates is easier. So that as key takeaway, okay, we can reduce the degree of freedom due to the physical object we want to inspect. By running coordinates in R to so-called holonomic constraints. And the holonomic constraint is defined as follows. We have a more or less nonlinear algebraic relation which couples some of the coordinates Q tilde with others. That's all. So X and Y are coupled. Remember? If I write down now the why we do it, so in brute force,
we end up with r squared should be, or L1 squared should be x squared plus y squared of t. For every time instant t, this has to hold. And this is similar to what we see here. There's an algebraic relation, so I can put the L1 squared on the right-hand side and have exactly the expression which is on top here in the definition. Let me speak of polynomial constraints. And if you look at, well, typical mechanical examples, if you go to the fun part and, well, sitting in a roller coaster, you have zero constraint to the brakes, right? In some sense. Wouldn't be so funny to be a free moving object. The very same, but more difficult to describe, right? If you're circulating and spiraling and looping and all these things, so funny, but and holonomic. Also holonomic constraint. Okay, simple. I just want to further define holonomic constraints. These are constraints which are explicitly time dependent, so the constraint changes over time. Might happen, but it's a rare instance, right, where we see this in practice. But very often we have so-called real nomic constraints, real nomic constraints, sorry, vice versa. Real stereonomic constraints we have, and real nomic constraints we don't have, because this time dependence is very hard in spectrum. Okay, so then we see so-called non-polynomial constraints also. This the second, and the definition is a little bit strange. It's as follows: these constraints can be represented as algebraic relation. So it's a it can be represented in such a form. I want to give you, so what do we have in mind? So first, okay, all inequalities. A simple example that you have in your car or even in, on your bike, if you have a dead bike, front axle, and then it can go anywhere, and at some point it's made this into the car or into the ground. So there's some sort of constraint in terms of x direction. Here, for example, in this example, this plate smashes into this fixture here, means that x has to be always greater than 0. It's obviously not a representation as an equation. It's one way of it. But there are also strange things which are occurring. For example, if you're bicycling, can you do everything with the bicycle in terms of moving into every direction? Is it possible? No? I would say yes. You can't fly up, yes, of course, yes, unfortunately. But you can't fly, but for other reasons. But if you're saying you're in XY direction, so just on a plane, and we do not considering the Z direction, can you move everywhere in XY position?
So the y velocity of your rear wheel is always 0.
Yes, that's true. Something else? Can you move at every time instant to make it more precise? Can you move with your bicycle at every time instant to every position?
As we said, we can't really go sideways directly, and we have also dynamics, so we are already traveling in one direction. That's,
yeah,
we can't just instantaneously switch direction.
Would you be surprised to close the door to means also the discussion of ours? It works. Perfect, thank you. That's it. You can just jump to go over there. You as a human, you are able to do that, right? You turn, and you can do a side step. The bicycle can't do this.
waves become sterner. That's interesting. It's like a rolling penny. A penny can only roll on the surface. It's simple. It's similar to the one we have. A penny which is standing up and should roll, it always rolls first in the direction the penny directs to, right? That's the very same for a bicycle. You can do, and the reason for that is physically what?
First law.
Newton's, yeah, I don't want to understand the physics, but if you look at the bicycle, which part of the bicycle is responsible for that? You can't go anywhere. What do you think? The same applies to cars, by the way, usually. Not every car, but almost every car.
Direction of the front wheel.
No, if I turn it, I can move with the front wheel almost everywhere. It's obviously the rear wheel because it's fixed. If you have a car with four wheels steering, for example, we have such a thing at our institute where you do four wheel steering. Every wheel can be steered everywhere. Some steering positions do not make sense. It's like skiing, looking like this. Okay, this does not make so much sense for cars because we are braking with that. We by the way did a study for a big automotive company whether we can brake with such a way instead of using traditional brakes. Does not work sufficiently well. So, but it's possible. You can brake. Why it's important for autonomous driving? You need some sort of a safe situation in some situation. But if you have a four-wheel steering situation, you can move sideways. Next time I'm bringing this. Yeah.
Does it all steering vehicle have the autonomic vehicle?
It's called autonomic wheel, yes.
Even if you consider that you can't rotate the wheels like immediately.
Yeah, that's different. Yeah, but in this case, if you make it, it's always a kind of question of abstraction. You know, if you say, okay, I can turn the wheels instantaneously from forward position to leftward position. Of course, you're right. Then you have to first turn, then the dynamics somehow will constrain it. But for a more abstract version, we discussed here, turns instantaneously into that direction. And therefore, these kind of wheels are very often called, now you know the name, holonomic vehicles. There are also specific wheels which you sometimes see at robots, which allow the sideway warp also, but it's more or less a holonomic vehicle. Our traditional vehicles do not have this situation. We cannot go everywhere at this point. And I want to describe where it comes from physically. But you know, it's a rear axle, which is fixed. So now here is the penny, which has the same situation. If it rolls, this is the mathematical description here. You have an x, y, z coordinates. To describe the rolling, we have a phi coordinate because it rotates. And there's an important fact which we have to consider is that the penny does not slip. To make it easier at that point. Okay, and then I define, okay, there's an angle theta, which describes the direction of the penny, and then the movement of the penny, this is not well depicted here, is the v, the velocity in forward direction, right? So with these parameters all together, I can describe the principal movement of the penny. And not slipping means that this point is in contact every rotation is always transformed into forward movement into the V direction. Obviously, as you know, with your bicycle, but also with the vehicle, with a certain amount of movements, you can reach any position, right? But not instantaneously. That's the very difference. And now we see where the constraint comes from. So first of all, the first constraint says that the movement forward is completely governed by the rotation. So we can say, okay, the velocity, the absolute value of the velocity is r times phi dot. Clear. That's the first thing. Then it must be perpendicular to the wheel axis. That's also clear. That's the definition of bend. That's the definition of the movement. So we can say x dot is equal to v, absolute value of v, times cosine theta. Or we can write it down using this formula: x dot minus r phi dot times cosine theta has to be 0. The same applies for y dot. If you do the calculation, so it's just summing up the equation for velocities. And now I want to do the following. Here, there is obviously a connection between the x dot variables and the phi dot variables, right? That's interesting. That's different to what we've seen before. Here, the derivatives are constrained. And to make it even more explicit, I take the first formula and write it a little bit different. So sorry for the for losing mathematical rigor at that point. This transforms to equal to 0 can also be rewritten in this form, and think of the phi as small portions of phi, or small portions of x. But don't talk to mathematicians; they do not like this. But I think it gives physical insights into it. There is a constraint of small portions of x directions relates to small portions of phi, and there we are. So physically speaking means that there's a constraint in the derivatives there's a constraint on the infinitesimal values of the x and phi values of the state variables, right? And these are called also non-holonomic constraints. So if we look at the overall situation, we have two types of non-holonomic constraints. One is given by inequality, and the second is given by such things here like infinitesimal equalities. These are the two ways of having that. And this makes it a little bit more difficult to describe these things, because with such objects you can't do everything, as you know from daily bicycling. You can't go left hand if you want to do. You have to go first forward. The funny thing about these type of systems, the general rule applies, this applies in general. On a global level, can go everywhere. That's the way. So with the bicycle and the car, can go everywhere, almost everywhere. And some forces, but so you can go from A to B, but you have to do U-turns or even two turns. That's the interesting fact. So we have to consider those facts to make it a little bit more generalized. Then you find something like this. Linear non-holonomic constraints can be described as the sum of the dot variables of the Q values plus a constant. That's the way how it goes. That's the generalization of what we see here. for linear case. Then we have the most difficult situations where the non-holomorphic constraint can be also non-linear. But we want to check it both. Well, now we come to use the equations of motion right now. The equations of motion means I always want to. Motion means the equations of motion mean the equations of every physical object. So hydraulic, pneumatic, electrical, and mechanical. That's important. So because it applies always to everything. That's the interesting one. And there are two ways to learn that. The first is the differential principle. It's the way D'Alembert did it. And then there is a integral principle, which goes back to Hamilton. And if you think of the first, it's all straightforward, but unfortunately mathematically not justifiable. That's the problem. The second is mathematically correct, and also, well, we can do the calculations correctly. We do both because I think starting with this intuitive definition and then seeing what's happening is also interesting. But you're in contract, and that's what the mechanical engineers learn in the third semester. And you learn something about optimization of systems, and therefore you can do the second also, which is not possible without such a lecture, which usually is taught in the master degree. Okay, so let me start with the first, because I find it very funny how it works. So if you want to check how an object behaves, what do you do? Well, I observed my son when he was very young, what he did with his blocks and buildings, and then he checked whether the building is stable. Well, the simplest thing is to smash against it, to shake it, to move around. And I think that's the principle. If you understand that, you can understand D'Alembert's principle. That's it. Just shaking the physical object and looking what happens. That's what you do, or what you did when you were there. And we do the very same, but now not really in the physical world, but we do it virtually. And to make it a little bit more complex, and my son needs some time to shape it, you do it in 0 amount of time. That's our consideration. So we do the very same, small kids are doing and learning how the world behaves, but we do it in our heads virtually 0 amount of time. That's the way we learn it. And we do it in a small portion of movement, in contrast to what my son did. Okay. If so, then you have an infinitesimal coordinate change, which has to be somehow compatible with the constraints and is instantaneously executed. And to describe this, we use this Greek symbol delta as given here. In contrast, what we know from infinitesimal portions of a variable, where we always write a d. So be aware of that. They make it an example of what we want to do, just as to learn it by heart. Delta is somehow virtual, and d is a real displacement. So to distinguish the two, we need that later on to describe the mathematics correctly. Okay, so then virtual the real, to make it a little bit more explicit, so let's say you're staying in an elevator, going up, that's you, and you're moving around in the elevator, and now you want to look at the virtual displacement and the real displacement. So infinitesimal movement. So obviously you are somehow constrained to stay in the elevator. So if the elevator goes up, you also go up. And now we want to describe the real displacement, which is obviously dx, so your personal movement, small portion of it, and the small portion of the movement of the elevator, which is the z direction, right? So we end up with v0 times dt. That's the small movement displacement of an elevator. Okay, we will see why we didn't need it. If I do it virtually, we have just the virtual component, the delta x, and due to the fact that we just do it virtually and as maximally fast, delta 2 is equal to 0, which means that, yeah, this coordinate is 0. Okay. So that's the description. So we have differences in the virtual displacement and real displacement in the small portion. Now, instead of looking at, let's start it like this. I just want to start with a simple system which just consists of, it's a network, and here's a typo, should be circuit. So suppose you have an equivalent circuit, which consists of just capacitors, to make it simple, and sources. Now, that's the situation. So usually you have a network of capacitors and some sources, and the interesting fact and the question, which is our guiding question, is the question from the very beginning, and we want to use all the things we learned about virtual displacement of it. So what we do is we use the network of capacitors, and we want to get rid of the intermediate flows, right? So if you think of something like that, here you have a source of flow, and then some capacitors here and there and there and there perhaps, and here may look like this. Okay, so if you do classical equivalent circuit calculations, you have to calculate all the flows, right? In between. And at the very end, you all together to one set of equations. And what I depict here in the middle is just one capacitor, perhaps this one here. And I want to describe the entire relations of how it behaves by virtual displacement. And we need some definitions like that. But what is important and what you should learn here is we can perhaps say, okay, there's a flow which goes into the capacitor driven by other force flows here. Okay. And we can distinguish virtually in our brain the flows into two parts. There are some flows which are just due to the network, because there are other elements which are also driving this simple capacitor. But there's one flow in this specific, or some portion of the flow. So we are looking at this object here. There's some flows which are driving the capacitor from outside. So our source of flow is given on the left-hand side, and the question is how much of the source of flow on the left-hand side in this example is driving the capacitor. That's the question, right? So we're this specific, the blue one. So we can virtually describe the flows in two parts, Ki, which is driving flow, which are the driving flows, And then there imaginary some constraint flows which are just, well, describing the network more. And with that, we can describe the entire thing. That's the interesting part. So we split all the things which are going on there in the network, and with that we describe all the capacitors. Therefore, the index I, just to understand. If we did it, well, you will see we end up with a nice formulation of the equation. So we have just all the capacitors. So in this specific example, we have 1, 2, 3, 4, 5 capacitors which are in the network, and we have I going from 1 to 5. That's it. And I just look at one specific capacitor to do the calculations. So remember that. Okay. So if we do that, we know Kirchhoff's current laws. We can say that the flow I tilde, because we do not just know the redundancy situation, is equal to Zi plus Ki. And we also know that this flow can be described as a coordinate variable derived integration. That's it. And this is given by Ci times Pi dot tilde. That's the definition of a capacitor. So capacitor times the capacitance effort variable derived is the flow. That's something you learned in electrical engineering in the first semester. Nothing new at that point. So rewriting this equation gives also Zi plus Ki minus the QFI tilde dot is equal to 0. Just reformulation. If we now do the following, we take a virtual displacement of every capacitor. So we shake it a little bit. That's the idea. In the position, so QEI tilde, and we multiply the equation that still holds. So it's just the virtual displacement. And now we need an additional definition. We define virtual work as delta Wi being Fi, so a flow times the displacement. So it's a small portion of work. And now let's see what happens if we do so. So first of all, we get the following. With this, for all capacitors, the following equation holds. If we sum 0 up, we get this equation. Okay? So for every capacitor, 0 plus 0 plus 0 gives 0. It's simple. It's just for all capacitors. So for all redundant coordinates, NR, I goes from 1 to NR. We have to do the very same. And then we can split the equation and collect all the parts which belong to driving flows and those which are interior flows, so in the network. The driving flows are due to the external source. With that, there is a principle which is called the principle of virtual work. The principle of virtual work says if you virtually shape the flows which are in the network, it does not produce work at all. This is by empirical evidence, because if it would produce, if it produced work, it would have to be up, right? So, and the table is called, so, and there is a mathematical non-rigor that this can't be proved in that sense. So we assume that this holds. There's some political observation, but so not very rigorous. Please believe me, that's true. If we make this a function, then we end up with the following thing. That is very nice. A so-called D'Alembert's principle. It says if we sum up the external flows minus the QFI tilde dot times delta QEI is equal to 0. That's it, and we are fine. That's the equation of motion. And we would say, And what do I do with that? Can I do any calculations? It's easy. How do I work with it? But it's the first step towards the final solution. And unfortunately, you know, what we see here, we only have the external flows in our equation. So the interesting fact is that with this simple trick, we got rid of all internal flows, right? They disappeared. We do not have any internal flow in this equation. So if we are able to solve this equation, we get the equation of motion, obviously. That's control. That's wonderful. So all internal intermediate variables which make the calculations so problematic disappear. But there's unfortunately a downside which is problematic with this equation at that point. There's still variables which are tilde variables, so there might be independence between the variables. So the question is, because there we have redundant coordinates, QFI tilde and QEI tilde. And remember, there's still these sign signals that they are somehow coupled. Well, and now the very important assumption comes. If you know the way the variables are coupled, I mean, QEI tilde and QFI tilde, if you know how they are coupled, then you can do the calculation. So, remember the pendulum? Okay, I know the coupling because the drum base is on a circle. There the coupling is present, right? So QEI tilde is given the coupling of these variables. And this is the situation which you see very often, that you know the coupling, particularly in physical and mechanical objects. If you look at mechanical objects, you know the coupling because you inspect your object and you see, okay, it moves on a circle, it moves on a spiral, it moves on in a loop or whatever. So that's the interesting fact. So if you know the coupling, but this is the problem at that point, and that's the problem what you have to learn later. Where is the coupling? How do I find out what coupling is there? So keep that in mind. But for that moment, we assume that we know the coupling. We know the coupling between the variables. What does it mean? We know the holonomic constraints. At that point position, we say, okay, non-holonomic is difficult, even also. First step is without non-holonomic constraints. First, it works also with non-holonomic constraints, but for our consideration, we just think of holonomic constraints to make it easier to do these equations. What does it mean? Okay, the holonomic constraints are given. This is a function HA, which couples some of the variables QEI. Not to forget it. That's it. So what we can say, we can express some of the variables QEI tilde by other variables. That's it. And now the question appears, what happens if I have this knowledge? If I enter this knowledge, if I know HA, if I enter this into this equation, what happens with that? How does it change? Well, the last semesters, so 2 or 3 years ago, I always did the calculations for you. They are here. And just to go back, just to show, this is just mathematical reformulation of the same thing. Nothing special about it. And nothing tricky. The only thing what you do is you enter this knowledge into the very beginning, the equation, for Dalander's principle. You just enter it. So if you're interested how the equations at the very end, if I see the slides here, are deduced, please read the supplementary material. But it's nothing mysterious, even if the equations look all to you. It's nothing mysterious about it. You do just derivative operations, you collect some terms, you decouple some terms. It's just math, simple math at that point. So follow these calculations. At the very end, the interesting fact is, here is it, you end up with the following equation. If you do so, and you enter these polynomial constraints, you can calculate the equations of motion, the equations of how the system behaves, your state equations at the very end, by a set of simple formulae given here. And these formulae, the formula for one specific J looks as follows. You have to derive partially the total energy of the system. The T, remember, T is the symbol for kinetic energy. You derive the kinetic energy with respect to QEJ dot. So it's nothing else than the derivative of the accumulated FO variable. So remember the FO variable in for mechanical objects is what? Do you remember that? FO variable for mechanical objects. The FO variable. The flow variable is force. The FO variable is velocity. So the velocity integrated is displacement. The displacement divides velocity. So when you do it, you write energy with respect to velocity. That's it. Just to make it a little bit more explicit. Here, and subtract, and then do a time derivative of the result. Second, do a derivative of the kinetic energy with respect to position, to displacement. Subtract the external flows, so forces. Remember, flow is force in mechanical. And this is equal to 0. That's it. The total energy of the system is simple, isn't it? Because we just look at the old storage elements. If you think of a mechanical object, you just have to collect all kinetic energies. So typically the masses which are moving around. And here comes the funny thing, which is deduced on the slide before, so it's something for you at home if you like. You sum up just all redundant storages. You sum up everything you have. And this is the wonderful fact. So if you take, well, you have a mechanical object, for example, with masses which are coupled in some sense because they are interrelated between each other. But you take them all, you calculate the energy, you put it in that formula, and you get the equations of motion. That's it. And therefore, I say it's very simple. The interesting fact is it also applies for electrical systems. It also applies for pneumatic systems. It also applies for ground systems. Just a second. Well, just sum up the kinetic energy and then do the calculations with the derivatives here, and that's it. Then we are happy. Now we do the question.
What happens if you add springs, for example?
Yes, that's the next point. Well, up to now, we are just going on with capacitors, with meaning, well, we just have multiple valves, and that's perhaps nothing we want to deal with in practical situation, because we have springs and all these. We also have dissipative elements, which might be also present, so friction in mechanical objects and resistors in electrical or dissipative elements in pipes, so you have to also to be able to describe that. But for the first moment, take it as it is. And I want to make it a simple example, because you, back to that, mechanical engineers learn that for mechanical objects. And they learn, well, this formula for kinetic energy. Kinetic energy, as you know, you have to but the interesting fact is it also applies for electrical systems. And I want to show you this example for electrical and one electrical system. And this is one I mentioned one of the last lectures, where we have two capacitors in parallel. Just to simplify, simply show, well, we have two capacitors. And this also shows that we have to be aware where the problem is with that, and what also defines the beauty. So we have, again, both sides. Again, the source of flow to capacitors with two F4 variables, E1 and E2. And what we do right now is we just sum up all the energies. We know that the energy of capacitors is a half C1 E1 squared. That's it. This applies also to the second, a half C2 E2 squared. And this is the sum of all energies. More storage elements are not present in this circuit diagram. Now, the important fact comes, we know that E1 and E2 are equal, so here's the holonomic constraint. So we write down a half C1 plus C2 times E squared here. Now put everything into the formula and derive with respect to the non-redundant coordinate QE dot and QE. What is QE dot? It's the integral. The QE is the integral of E, or the flux linkage in our case for the electrical system. But we will see. So here I do the calculations first, and then we see what happens. So okay, first take the derivative of a half C1 plus C2 QE dot squared, which is the equivalent of the E squared QE dot, the same. By definition, I have to derive with respect to QE dot, and then do the time derivative, and here the second with respect to QE, and this has to equate to F. Okay, so what do we get? This depends on QE dot, and this here does not depend on QE. Take it like in ODS, you learn it in there, take this as a variable. So derivative of this expression with respect to QE, partial derivative, and therefore it is correct, this is 0. And the first one is a simple derivative with respect to QE dot, which gives you here, gives obviously this expression, C1 plus C2 QE dot, and this has to be derived once with respect to time. I get QE double dot. And this equates to 0, so obviously C1 plus C2 E dot equal to F. Not very surprising, we can expect whether this result is what we should have expected from our electrical engineering experience. We would say, well, this is a parallel connection of two capacitors. Let's do first the parallel connection. C1 plus C2 is the capacitance of both capacitors. We know the voltage over both capacitors is equal to E. Consequently, we would expect that the total capacitance times the dot should be equal to R. That's not surprising, it's a simple example, but it shows, well, you can start with the regarded coordinates, with the regarded system. You sum it up, you sum your energy up, and you equate to give equal to the external forces, and that's it. That's the funny and wonderful thing of it. What are the key takeaways? First key takeaway is, well, obviously, the dynamics is completely defined by the energy storage. It's here we have it explicitly present. So the dynamics of any system in the world is given by the energy, defined by the energy storages. And energy is the how the energy behaves. What kind of storage principle defines how the movement is? It's the first part. Second, if I know the holonomic constraints, I can easily calculate the dynamics of motion for every physical object as far as it can be described by long parameters. Simple. And then I put everything into this formula. So there's one assumption, if I know the holonomic constraints. There's the problem. So sometimes I know, sometimes I do not know. But if I know the assumption, if I know it, I'm fine. Cycle mark. No, let's go on with the three takeaways. Third, this is a straightforward procedure, but we should know the energy. And up to now, I wasn't precise because I said, take the energy, but this is not true. We have to take the full energy. Do you remember under which condition the full energy and the energy deviate? Yes, if it's nonlinear. So if we have nonlinear storage element laws, then we have to consider the full energy. Important. That's the difference between mechanical and electrical engineers, mechanical and thermal engineers. Because the mechanical engineers just have kinetic energy. They can say T star is always T. I'm happy. You, unfortunately, then you're working in all domains. There might be nonlinearities in the storage elements. Be aware of that. Say T star. Important. It's not a mysterious problem, but be aware of that. There is a T star. Therefore, if you look at theoretical mechanics books, very often T star is omitted and replaced by just T. But this is not true. Depends on the domain. Well, up to now, we still have a problem because we just, last remark, as you mentioned, there are strings missing, dissipative elements missing. So we should somehow introduce springs and or inductances and dissipative elements like resistors. It's also important. So that's the part we have to do. But with that, we get this result. Okay. So one question. Do you know this formula? From where? Similar to OVS. Here this in mind. Similar or equal? It's equal to some equation in OVS. Do you remember which one? Even here on the slide, the Euler-Lagrange differential equation. What does the Euler-Lagrange differential equation solve? Just a single from the question.
Here's how we are.
An optimal path problem, a dynamic optimization problem. So by re-engineering, looking at this equation, obviously there might be some sort of connection to an optimal optimization, to an optimization problem, right? So there might be something like an optimization problem. We will look at this hopefully today. This is the last remark at that point. You see, okay, this is a Euler-Lagrange differential equation. I know that from dynamic optimization. I learned that with that, dynamic optimization problems are solved, and we get some sort of path out of it. It's not so. It's not surprising we get the path of motion, right? But to which optimization criteria? That's the fun question, the interesting question, which we want to look at in some slides later. So there's still some deficiencies. One is, well, how to introduce springs, so the inductive elements, and discipline elements. That's the first step, and then we want to reinterpret this situation. Okay. So first start with the inductions. Well, the simplest trick to introduce them, it's very simple, therefore I do it here. We can say, okay, every external flow that can be separated into three parts: the sources, inductors, and resistors. That's it. And then we try to describe the flows coming from inductors or inductances. There's an S missing, I think. Here. And resistors have to be described. That's it. Okay. We know R is, so the resistance or linear resistance we very often can describe the flow. So there's a relation between the flows and F variables, right? Second, the inductances, there we know there is also a relation of the the flow variables and the stored energy in the inductance, and that's the expression given here. If you look into chapter 2, where I define the energies of inductances and capacitors, I already related the flow and effort variables to the various energy variables. So if I derive the stored energy in inductance storage with respect to the generalized variable QEJ, then I get the flow. So you can test it with your electrical engineering knowledge for the cell inductance. And you will end up with this expression. And with that, I just put this here and say, okay, then we get this equation. This is the so-called Euler-Lagrange differential equation, or Lagrange equations of the second kind, which is given here. It reads as follows. It's similar to what we had before, but in contrast to the situation before, we looked here at just the kinetic energy. Now we have the difference between the kinetic energy and the potential energy. And that's what mechanical engineers should learn by heart. If you wake them up to 2 o'clock in the morning, they should say, what is Lagrangian? And he says, kinetic binding potential. What you should learn is co-energy of capacitor storages minus energy of inductive storages. Because you have to be aware of this co-energy thing. So it's T star minus mu, unfortunately. Well, this is the way we can do it. With that, you have everything in your hand. You just formulate, and it's the very same. U is the sum of all storage elements. So again, I wasn't very clear. This is, and U should be defined here. U is equal to the sum of I 1 to NR tilde and redundant UI. So all storages are summed up. So it's same principle like for the capacitors. You take all inductances, collect them, sum the energy formula up, put it here, define it as U, apply your machinery of Euler-Lagrange differential equation, and you get the equation next. The only problem is the if you know the holonomic constraints. That's the only problem. About this, I want to talk, before we go to the Hamilton principle, but first of all, well, why are holonomic constraints easier to grasp than just the interrelation between those? Because the geometrical, in particular, if you look at mechanical physics, it's easy because you see the movement of what you want to construct. You know, it's constrained to that, to that, to that. So the main task is to inspect the object and see, oh, these are the holonomic constraints. And that's what the mechanical engineers learn. First thing. Second, you can write down these equations in different coordinate systems. You can write it down in polar coordinates, in X, Y, planet coordinates, whatever you like. In some of the coordinates, it becomes a tedious calculation, and some of the coordinates, it's okay, it's easy. So think of the pendulum. If you derive it in polar coordinates, it's easy. If you derive the equations in X, Y coordinates, it also works. It's simpler. But then it becomes difficult, more difficult, because you have to enter always the square root of r squared minus y squared into your equations. And you see, if I do all the derivatives, it's not so funny. That's the problem. But there's so when I started to learn something about that, I during my student life, the professor said, "Hey, here is a coordinate system," and I said, "Where?" Because I was used to think in Euclidean space, X, Y, Z, and I was happy with that. And he never explained that finding the right, there is no right coordinate system. There is always all coordinate systems are possible, but they're coordinate systems which are easier to calculate than others. And that's what you should take and have as a takeaway. For me, it was difficult. After a while, I realized, no, there was nothing mysterious about it. He has some practice to find the so-called right coordinate system because he practiced doing Euler-Lagrange mechanics since 20 years. And if he looks at the object and says, okay, it's this crazy coordinate system which is easy to use. So for me as a student, it's not easy to use because I have not practiced it too much. So if you want to get the right coordinate system, it's more or less some sort of training. It's nothing special where you can look at it a bit and say, okay, this is the best one. But every coordinate system is okay. That's important. Which means that if you see and do the calculation and see, oh, it's difficult, it's problematic, and I have to do all the calculations that become complex, then sometimes think of choosing another coordinate system. That's the way to do it. If my calculations become overly complex, I go back to the start point and try to reduce complexity by redefinition of the coordinate system. But it always ends up here. So this if problem is if you see the coordinate and if you see the holonomic constraints, then it's nice. Because you have to do something like in our example, you have to define what is the holonomic constraint. And in the exercise lecture, you will learn, so there's a 3-step procedure. If you do the calculations through it, please always look for the right coordinate system, look for the holonomic constraints. What is coupled? And the question for you, we learned a method to find out what storages are coupled. Do you remember that? One of the last lectures in chapter 2. But just a word or just picture you have perhaps in mind to remember the situation. We have the same situation for finding the same space variables. Exactly. So we look at this connected trees and graphs, and then we found out what kind of variables depend on each other. So if we have the network present, you can say which are the redundant and non-redundant objects. So it's always a lead balance. So for electrical engineers, it's good. Please do not tell the so if you put it in this equivalent circuit diagram, you find it easily. If you put it in a bar graph notation, you find it easily. Do not tell this easy way of calculating networks to the students in the first semester doing still the equivalent circuit calculations with pictures of vertical voltage and power loss. Because the number of calculations you have to do here is substantially reduced compared to, well, inserting into this equation, inserting into that equation, inserting into that equation, in several from here, well, writing down the energies, then easy. Okay. So what you have to train, and this is what I asked you during our exercise, our exam, or exam, you have first find out some sort of where are the holonomic constraints. This is the typical question, and the typical question is also which kind of energy storages are present, not to forget something. This is the problem at hand. And what you have to train during the exercises, well, if you have a physical object, look at it and say, okay, these are my storage elements. And if so, then the procedure is quite, well, straightforward. You can program it mathematically, and that's that the computer do the calculations with symbolic computation. Okay. This is the part for the practical things. You have to train it a little bit, find out the equations, and then we get to the equation information. Wonderful. So at the very end, putting a little bit more insight into the story, you already realize that there is a connection to optimization. There's an optimization principle obviously behind, right? And well, this observation was also an observation physics did, and the following interesting fact appeared into or popped up. If you have a pointless point mass which moves from A to B, or for example from here to there. And we assume that the mass arrives at the same amount of time at the same position. What trajectory would the mass take? And the interesting fact is what one observes is that the average kinetic energy minus the average potential energy is minimized. So if you take the average of the kinetic energy, which is, well, how do I get the time average of the energy is integrate the energy over time divided by the time spent, right? So that's what you see here. We minimize 1 over T0, TE minus T0, and take the minimum of this. And then we're fine. So what, and that's an observation, and which has been done in physics, and so nature behaves according to an optimization principle. I found it very funny, interesting, and the funny thing, I mentioned that at ODS also, that humans behave according to optimization principles, but also physics. And here is the fact. So physics minimizes the average potential energy minus the average, the average kinetic energy minus average potential. Okay. That's what is done. There's a wonderful lecture by Feynman who did this, and he discovered this in at school already, guided by the physics teacher, because the physics teacher realized that this that Feynman is a little bit more ahead of the other students, so to say, and he told him that and was completely fascinated. And then he tried out the term, this curve, and that curve, and that curve, and he always did by hand calculations, the integral and not the integrals, but summed up, could that be related? And that's how it works, how research works, and how we play around it. But that's what he did. And also later on, and defining and describing some sort of quantum mechanics and some sort of integrals, they somehow back to that. And I found it also a very, very very dense description of how physics works. And this applies not just to physical motion or mechanics, but also again mathematics and physics. So now made it a little bit more explicit. We then define action. Now, action is the integral of the kinetic minus the potential energy. So that's the way it was firstly defined. And if we minimize action, we get the equations of motion. Obviously, it does not depend on the difference between T minus T0. Why? Because a multiplication of a optimization problem with a constant gives the same result. We remember that. So whether I add here 1 over T minus T0 doesn't change the rule, just to make it a little bit more explicit. So now you remember the ODS lecture, hopefully, what we did to get the equations of motion, we played around with the different, or how to solve such kind of problems to minimize the action with respect to the various variables which are present. So our aim is to minimize S. Then we can apply all the tools we learned there. So it's Euler-Lagrange in Hamilton, you remember, right? Two different descriptions of the same thing. We end up with the Euler-Lagrange differential equations. Oops. It's exactly what we deduced with these vibration principle, the virtual displacement thing. We end up with the same thing. And if you remember, and this is just a recap for you, just a copy some of the slides from ODS, so to repeat the topic. If you remember, in general terms, we start with the more complex situation. We have an objective function, and we try to minimize this part and this part, so final values and the state trajectory, and we learned how to do that. And if you remember how we get how we got the differential equations, so they Euler-Lagrange differential equations, and remember perhaps we varied the different trajectories. So I go back to this picture, perhaps you remember that. So we thought of taking the minimum and deviated this minimum trajectory by adding some additional values. So that was the idea, and then we compared it with the intrigue strip of Euler and Lagrange to do it that way. And at the very end, we are now by minimizing this thing, and that's perhaps in between. I should put this out of the recap equations, sometimes also written as delta J, not to be confused with this virtual displacement thing. Sorry for that, but in the books it's the same symbol. So if we minimize this, so what we can say is the ultimate trajectory is given if the first variation is stationary. So saying is equal to 0. That's what we learned already in ODS. And we end up with the Euler-Lagrange differential equation as before. So we got the right the equations out of the Euler-Lagrange differential equation. That's it. And there's a close connection to an optimization principle. That's a funny or interesting thing. Which brings us to a simple example again. I just want to take a mechanical example to show you that it really works out. So suppose think of the example with the point mass. So moving around, but governed by gravitational force. How is the equation of motion derived? So we have to minimize over x the action values. Now let's define the action. Action at that point is exactly the Lagrange function. So kinetic minus potential. Remember that. Kinetic minus potential. Now we put everything in the Lagrange differential equation, which is given here. Here, L is given. So T minus U equal to L. So we do the derivatives of that. The very same here. And if we do so, we get the first equation solved. So I go back. Your derivative with respect to x dot. Well, we have the here expression. This does not depend on x dot. Sorry, there is a mistake. Should go over here. Obviously, we get 2 times x dot times n divided by 2 gives m x dot. Here we get an expression with respect to x, which is mg, so we get d dt of mx dot minus mg is equal to 0, and not surprisingly, x double dot is equal to the gravitational acceleration. So interesting movement. So this is the story behind. More justification for everything. The variation in principle tells us equations of motion are governed by some sort of are governed by energy. Second, they are governed by optimality principle, and very simple. You get the equations of motion by just putting it into your machinery often that are actually differential equation or Hamilton equation for the line more. Why it's easy? Because it's straightforward. You don't have to do, well, if you ask mechanical engineers what they have to calculate, they have to read the body, show the body diagrams with all the forces and all that. Here, we just put the energies together, do the calculation, and then that's it. It's even more interesting if you think of systems which are working in different domains, right? Because if this is true for mechanics, hydraulics, pneumatics, for energy storages in each domain, put it into the equation, solve the equations, that's it, we get the power system. And that's what we're trying in the exercise today. Bye bye.